On October 31st, 2025, 3 Chinese astronauts boarded Tiangong, ready for routine science and national pride. But as fresh experiments began, news arrived that the Shenzhou 20 return capsule was damaged, possibly by space debris. Suddenly, safe passage home was uncertain, and the world watched to see if China's space ambitions might leave its own crew stranded. What unfolded next would challenge the limits of space survival. November 3rd, 2025. Mission Control issued a direct hold on all Shenzhou 20 return preparations after engineers flagged a suspicious anomaly during a routine capsule inspection. A hairline crack, barely visible, traced across one of the capsule's viewport windows. The order was clear: delay. Return until capsule integrity is fully certified. Telemetry logs and visual checks were launched in parallel. China manned space agency ground teams began reviewing debris tracking data, cross-referencing with NORAD and domestic sensor networks. Flight directors convened a rapid response committee, looping in propulsion, life support, and crew safety experts. The official statement emphasized safety above all else, but inside Mission Control, the clock was ticking. Every hour, the Shenzhou 20 crew remained aboard. Tiangong systems faced mounting pressure. The decision to postpone re-entry was unprecedented for China's program, and it set off a chain of contingency protocols that would soon test the limits of both engineering and human resolve. In low Earth orbit, the tiniest fragment can become a lethal projectile. A 1 millimeter piece of debris, traveling at 10 kilometers per second, carries the same energy as a .45 caliber bullet. The physics is simple, but unforgiving. Kinetic energy is 1/2 times mass times velocity squared. At these speeds, even a fleck of paint can punch through metal or shatter glass. Every year, the number of catalogued objects in orbit grows. The European Space Agency now tracks more than 36,500 pieces larger than 10 centimeters, but millions of smaller, untraceable fragments are out there. Collisions and anti-satellite tests have seeded low Earth orbit with debris, and new megaconstellations are adding thousands more. The space around Tiangong is becoming more crowded and hazardous with each launch. For the crew, a single unnoticed crack is not just a technical problem. It is a reminder of the invisible violence circling above our heads. Inside Tiangong, Zhang Hongjiang moved between experiment racks, logging data from the biological module. 4 live mice, each in a separate chamber, formed the heart of a study on microgravity's effects on mammalian physiology. Every feeding, every motion, even the mice's heartbeat patterns were tracked, adding to a growing record that would help shape future long-duration missions. The crew's routine was anything but simple. Every experiment had to be balanced against power draw, oxygen use, and the growing strain on shared systems. Wukong, the station's onboard AI, chimed in with regular prompts, reminders for environmental checks, risk assessments, and diagnostic cycles. When the debris incident forced the crew overlap, Wukong's advisories grew more frequent, flagging potential resource conflicts and suggesting schedule tweaks. For Zhang, the pressure was personal. Each delay in the research schedule meant recalibrating protocols and rechecking experiment baselines, all while knowing that every variable, down to the air the mice breathed, was now a precious resource. Life support logs began to tell a quiet story of mounting strain. With 6 astronauts sharing Tiangong's closed environment, oxygen and water reserves dropped at nearly double the usual rate. Engineers on the ground tracked the numbers hour by hour, watching the margins shrink. The station's automated systems flagged each deviation from the predicted usage curve, prompting status checks and conservation measures. Crew conferences grew longer, their tone more measured as Zhang Lu led discussions of prioritizing tasks and adjusting schedules. Routine maintenance was postponed. Non-essential experiments were rolled into future shifts, their data tables marked with new deadlines. Even small choices, when to exercise and how long to run the air scrubbers, became subjects of careful negotiation. Stress logs reviewed by mission psychologists reflected the weight of uncertainty. Wu Fei wrote that every breath and every sip has to be counted. As the days stretched on, the crew's resilience was tested not by a single failure, but by the slow, relentless arithmetic of survival. Launch opportunities to Tiangong are not just a matter of pressing a button. Every attempt to send a spacecraft from Jiuquan to the station depends on orbital phasing, Earth's rotation, and Tiangong's path lining up precisely. That window opens for only a few minutes each day, and sometimes not at all. If the station's orbit and the launch site fall out of sync, the next shot might be 2 or 3 days away. Mission planners map these intervals down to the second, knowing that a single missed window can stretch a tense standoff into a waiting game measured in days, not hours. Preparing a backup Shenzhou vehicle is not a matter of hours, but weeks. Every component, including life support, thermal protection, and guidance, must be recertified and loaded under strict protocols. Engineers at Jiuquan run through checklists that stretch for days, not minutes. Even in the best-case scenario, historical records show a minimum turnaround of nearly 2 weeks from initial order to launch readiness. Each delay compounds the risk, and every step is governed by the hard limits of orbital mechanics and hardware reliability. Space grows busier and more fragile every year. As more nations reach for the stars, global rescue readiness is no longer optional. It is survival. The next crisis could test us all.